to do a little primer review on hydraulic head. This is chapter 2 in the textbook, and we're just going to do a little bit on it. If you need more, you can contact me. I have more exercises and more sources for you. So we have here if you look at it, figure on the right shows a water standpipe. So we're going to take from this and think about a well in a little bit. We're going to start with a water standpipe. The bottom of the standpipe is 80 feet above sea level, and we're going to use that as our datum. A hose comes out of the side, and a siphon is started, and then we stop it. So now no water is moving in here, and the water levels are as shown. So we want to find out the heads and pressures at different points in the water here, and I have a table down here that we're going to fill in just a little bit. So I'm going to start with the energy equation, also known as the Bernoulli's equation. We could write Bernoulli's equation in terms of energy, like joules, but civil engineers don't want to deal with joules. They want to know, well, how many feet of water does that represent? So we represent everything by the feet of water. So the total energy, or the total head, is the potential energy plus the kinetic energy. The potential energy is two different forms. There's the elevation, we'll just use a Z for that, and then the pressure. So the pressure is P, and if we want to convert that to feet, we take that divided by the unit weight of water. Very tempted to teach hydraulics or fluid mechanics right here, but we're just going to do, like I said, a brief primer on this. That is the potential energy, both those terms. And then the kinetic energy, remember kinetic energy in physics, you always had a V squared in there somewhere, velocity squared. So in terms of head, V squared over 2G will give us feet or meters of head. So we'll call this the elevation head, this the pressure head, and the last term the velocity head. For hydrostatics, water not moving, so this water isn't moving, this term goes to 0. For static and in groundwater, the water is barely moving. So we're going to put that number to 0. If you're dealing with a pump system or something, you might have to consider the term, the kinetic energy term, the velocity head. But in general, in groundwater, that's going to be a 0. So the total head is the elevation head plus the pressure head. Again, that goes to 0. And the elevation head is just the elevation. The pressure head, it turns out, is the height of water or depth of water above whatever point we're looking at, plus any pressure that was there to start with. So we'll mention that. So let's move on to our exercise. Yeah, maybe I'll write down here again, total head. So let's look at our numbers down here. So I'll zoom out a little bit so you can see the whole thing. So what should we start with? Maybe we'll start at point A, at the bottom here. So point A is at an elevation of 80 feet. So I'm going to put that as the elevation head. We actually, for an unconfined aquifer, we can use any datum for that. So the elevation head is 80 feet. We could call this 0.0. We could call it 1,000. It doesn't really matter. Typically, when we do our underground storage tank sites, we go out there and survey a point and say, this is 1,000 feet. And if you've done site work, you might do the same thing. And then later on, if we get a point, we can connect that and get a true elevation, but it really doesn't matter. Just the relative elevation matters. So that's 80 feet. So the pressure head then is the height of water above there. So it looks like that's 15 feet. So at the bottom, it's 15 feet of pressure head. And then the total head is the elevation head plus the pressure head, or 95 feet. We'll come back to those pressures in just a little bit here. So let's do, let's go to the top here. Point D looks like it has an elevation of 80 plus 15. So it has an elevation of 95 feet. and it's at the water surface. It has 0 water above it, so it has a pressure head of 0. Now, this is assuming that this is open to the atmosphere. If this was sealed, like in a water tower that's put under pressure, you would actually have to add that to the pressure head. So when I say pressure head is the height of water above it, then that if it's open to the air, or in general, the pressure head at A is 15 feet higher than the pressure head at D. So the difference in pressure would be the H. So it's at 95 feet. So it's the same. Matter of fact, it's the same everywhere in the water for static conditions. So the water's not moving. We're going to have the same head everywhere in the water. Okay, so let's do point B is somewhere in between. So it has point B has an elevation of, looks like 85 feet, and it has 15 feet. So it looks like it's up to the top. It's 5 minus 5. Okay, so it's got 10 feet of water on top of there. So it's at a pressure head of 10 feet. So it's at 95 feet. Or again, the total head is the same throughout. All right, now point C is way up there. So it's looks like it's 85, 93 plus 13 is 106 elevation, 106 elevation. The pressure head, how much water does it have above? It doesn't have any, well, wait a minute. So how the water above it, so this is right here, that line where the water is, if this is all connected, again, remember this is sealed off here, if this is all connected, the water level shows us the total head. So it's actually, doesn't have water above it, it has water below it. So it's actually sucking up water. It's under suction or under a siphon. So we said that the water has to have the same head throughout if it's all connected. So it's 95 there. So I've given this problem as a quiz or something in other classes, and a lot of people refuse to believe this, but that actually ends up with a negative pressure head. So you have 11 feet negative pressure head, or 11 feet of suction head, 11 feet of siphon. So you can have a negative pressure head. As a matter of fact, that can be an issue if you're sucking up water. You have a negative if you're pulling a siphon, and actually it can crush the pipe. Actually, I got into the gravity-fed water business when some people were having a problem that their pipes were crushing in a gravity-fed water system that would go over a hill. So it would go downhill, then back up over a hill, it would get negative pressure, and they actually crush the pipe. So at some point, you enough suction on there, or really pressure from the outside, that crushes the pipe. And before you get that, you can get air locks, and you can get vaporization of the water and stuff like that. So that's a whole thing in hydraulics. And for those of you who had hydraulics, you know about that. But I'll come back to that in just a second here. All right, let's go through the pressure. So the pressure, if the pressure head equals P over gamma W, then the pressure would be equal gamma, that's the unit weight of water, times the head, H. And if you do that for the common system of units we use in the US, the gamma of water is 62.4 pounds per cubic foot. You multiply that by feet. We actually like to do things in PSI inches. So 12 inches per foot would be 144 inches squared per foot squared. So converting that to PI, you'd have 62.4 times H divided by 144. So you get 0.433, or another common number you might have in your head is that comes out to 2.31 feet of water per PSI. So if I take a pressure head of 15 divided by 2.31, I get 6.5 PSI gauge pressure. Did you follow all that? So if you just remember the 2.31 feet per PSI, 15 divided by 2.31, which is the same as 15 times 0.433. Again, I'm resisting the urge to go through the development of all this in fluid mechanics or hydraulics. Similarly, 10 times 0.433 or divided by 2.31 gives us 4.3 PSI gauge, G for gauge. This one is 0. And this one, negative pressure head, we get a negative gauge pressure. You can have a negative gauge pressure. Absolute pressure, gauge pressure is like if I put a gauge on it, it's measuring the pressure relative to the outside. So it's the atmospheric pressure plus whatever pressure the water is. Absolute pressure is relative to an absolute vacuum. So this would be the gauge pressure, gauge, apologize for my writing, I'm not very good at it here, plus the atmospheric pressure. Atmospheric pressure is going to be around 1 atmosphere or 14.7 psi. In this case, for this particular day, it's at 14.3, a little less than 1 atmosphere. So if I add 6.5 plus 14.3, that equals 20.8. And this one is 18.6. And this one is 0 plus 14.3 is 14.3. This one minus 4.8 plus a 14.3, you get a 9.5. So it's less than atmospheric pressure. You can have a negative gauge pressure. You cannot have a negative absolute pressure. So there is a limit to how far up you can suck water. So some pumps suck, but there's a limit to how much they can suck. And that's going to be about, so it goes to 0 if I convert the 14.7 psi times 2.31. It's like 34 feet minus the vapor pressure of water. So it's going to vaporize a little before that. So 30-ish feet is about, and it depends on the strength of your pipe or hose or whatever, 30-ish feet is about how much you can suck water up. So the deepest well you could possibly have is 30 feet. No, that doesn't make sense. No, I can put a pump down here and I can pump water up. I can push water up as far as my pump will do it. But I can't pull it up, siphon it up more than about 30 feet. And actually, if you get anywhere close to that, bad things happen. So there's something in pumping systems, the net positive suction head needed and available and for your pump and stuff. So it's something that's very critical in pump systems to watch for those low pressures because you can get cavitation in your pump. All right, so let's apply this to a groundwater situation. This is one of your homework problems. We're looking at a well here, and we have 3 wells, A, B, and C. Looks like they're 1,000 meters apart from each other, A, then B, then C. And we want to know these different quantities in there. So remember, up here, where the water level is standing, that's the total head. So it's relative to some datum. So in this case, the ground surface for A, it's 455 meters, and then we're going down. We are going to go down I'll write these numbers here for A. So this is at 455. This is for A, slightly different numbers for the other ones. And then the depth of piezometer, I don't know, what is that? Depth to water, the total head, the pressure head, the depth to water is 30 meters. All right, so we're going to go down 30 meters. So 455 minus 30, the total head then is going to be at 425. 425. And then the pressure head means the depth of piezometer. So we can call a well that's just there for measuring pressure a piezometer, pressure meter. We could also put an instrument down here to measure the pressure. So at the bottom of the well, that's what we're calling the depth of piezometer. So the depth of piezometer, we don't know that yet. We know the pressure head at the bottom is 57 meters. So that's the distance from the bottom up to the water level. The pressure head is the depth or the height of water above a point. So if the total head is 425, and the bottom of it is 57 meters below that, then the depth of piezometer, well, the depth of piezometer, first of all, 30 meters plus 57, I have that. That's 87, 87. And then the elevation head is going to be the 455 minus the 87, which gets us to 368. And my writing is failing me here. So that's what we're filling in here. And then, so we do that for all three of these, and then the hydraulic gradient here would be the total head at, if B is lower than A, which looks like it is, so it'd be the total head, the gradient is total head A minus total head B over the distance in between, which is 1,000 meters. And actually, to be more rigorous, I should have B minus A, and then that gives you a negative gradient. So groundwater flow is in the direction of negative gradient. But for grading this, I don't usually take off for the sign here. So we can come up with, this comes out to 0.023. I can say it's negative 0.023, or I can say it's 0.023 in direction of A to B. If your water is going uphill, you probably dropped a sign somewhere. So the gradient really is negative in direction of flow. But like I said, a lot of times we just say the number and then we say what direction it is. So finish out that homework problem on your own. I also copied and pasted it in here. This is a figure from the text showing the same thing in a little different language here. Basically, it's really showing the same thing there. Another look at it. And I also pasted in here, I think I did this and showed you on the first video here, again, the diagram of what a well looks like. So that's the first homework problem and a little review of hydrostatics and head. Then the next thing we'll move on to is Darcy's Law.